Cool. Okay. Thanks for having me. So the title of my talk is, does provable absence of barren plateaus imply classical simulability? A genuine question. And I put a genuine question there because there was some feedback after putting out the paper that people always think that when you give a question as a title of a paper, the obvious answer is yes. But actually in this case, it's a sort of yes, no, yine answer. It's somewhere in between. And yeah. Okay, so disclaimer. This talk contains a mix of sort of thoughts and insights accumulated over the last few years while studying the trainability of variational quantum computing schemes. So many of these insights that I'm going to present today have been mathematically formulated and proved. Some of them are open to interpretation. So one of the big sort of goals of this talk is not to make hard statements, but rather encourage people to discuss the hows and whys of variational algorithms and quantum machine learning. And this was very much a collaborative paper, a collaborative project. And many fun arguments were had in the making of the work. So I'm not going to read out everyone's name, but this is everyone on the paper. And I wouldn't say that we all agree with every single statement in the paper. It was impossible to get something written down that we all agreed with. But it was really fun and important that we had these discussions in order to produce it. And I put Marco in bigger because he really was the driving force in this. Okay, so today I'm going to talk about hybrid variational quantum computing, by which I mean any method that optimizes a quantum neural network, or equivalently known as a parameterized quantum circuit, by minimizing quantum cost function, potentially using training data. So this encapsulates I think all variational quantum algorithms and some, but not all, quantum machine learning methods. So I don't actually know the audience entirely here, but I imagine many of you are very familiar with variational quantum algorithms anyway. At least I'm largely going to presume that for this talk. But here's my 30-second summary in case anyone isn't. So the idea is that you have some parameterized quantum circuit. So that's going to be some quantum circuit with some arrangement of gates where some of the angles are parameterized. And then you can perform a measurement at the end, and that's going to give you your cost function with respect to a certain set of parameters. That cost is passed on to your classical computer. Your classical computer runs your favorite optimization algorithm, gradient descent, Bayesian optimization, whatever your favorite classical optimizer is, and tells the quantum computer what parameters to try next. And then you just keep on looping around using a hybrid quantum classical optimization loop. And then whatever your parameters are that minimize your cost, or maybe the minimal value of the cost you get, or the optimal circuit that minimizes cost, that's going to be, you're going to design your circuit, design your costs such that whatever you get out at the end of the optimization procedure, if all has worked nicely, is an approximate solution to whatever problem you're trying to solve. Okay, so this is a very, very popular and flexible framework. So I did a Google Scholar search for variational quantum algorithms, and I was surprised that I only got 1,450 results. Because if you look at sort of one of the review articles that's been put out on variational quantum algorithms in just 3 years, that's got over 2,000 citations. So actually the gap between those two numbers is interesting. Quantum machine learning, on the other hand, you've got 17K searches, hits. And okay, so why is the framework so flexible? Well, it's popular because it's flexible. So by picking your cost function, your parameterized quantum circuit appropriately, it's possible to massage all sorts of different algorithms into this framework. And it's relatively easy to do compared to sort of conventional quantum algorithms. You don't need to think so carefully about the structure of your circuit and how you're going to manipulate things. Instead, you just pick a cost, design your cost such that minimizing it can solve your target problem. So it's very popular, but people soon started realizing that actually training these algorithms was quite hard. So though it's easy to come up with a proposed algorithm, you've offloaded much of the hard work onto the training process. So there's many different ingredients to trainability. There's sort of the expressibility, so it's how likely it is that your parameterized quantum circuit obtains a solution. There's cost gradients and cost differences, and there's local minima, so the potential of getting trapped into poor local minima. Of these 3 different ingredients, the one I'm going to focus on today are cost gradients and differences. And what I'm going to talk about is how our hunt to try and find variational quantum algorithms with substantial cost gradients / differences, we sort of come up against the phantom of classical simulability, where maybe we've actually made the problem so easy that we can classically simulate it. Okay, so cost gradients. Hopefully it's pretty obvious that your cost landscape is going to need to be sufficiently featured in order to enable training. So variational contour algorithms, you're trying to minimize the cost. If you have significant gradients, you might be able to train. If you have negligible gradients, you're really going to struggle to try and find the minimum. And note that this is particularly an issue in the context of trying to minimize the quantum cost. So if you've got small gradients, then you're going to need high precision measurements in order to try and find the cost minimizing direction, figure out which way to go. But a quantum cost is measured statistically through shots. So 1/sigma² shots are required to estimate a cost to precision sigma. So this means when you've got small gradients, it becomes very, very resource intensive to train. And note that this is a big important difference with the classical case. So if you want to, classically, if you want, I don't know, to increase your precision by a factor of 2, you just need to increase 1 bit. Whereas here, increasing by a factor of 2, well, you've got this 1/sigma² scaling. So it's much, much, much more expensive. You don't have the exponential scaling precision that you have classically, you just linear scaling, well, quadratic scaling and precision. Added to which also shots are slow. That's a circuit you have to run on your quantum computer again and again and again. Okay, so assume people became aware of something called the band plateau phenomenon, where it was shown that for a wide range of different variational quantum algorithms, which ones I'll go on to in the next slide, you find that the variance in the partial derivative of the cost vanishes exponentially with the size of your problem. So n here is the number of qubits that your variational quantum circuit acts on. If you combine this with Chebyshev's inequality, what you get is that the probability of observing non-zero gradients vanishes exponentially with problem size, and so the number of shots required for training are also going to grow exponentially with problem size. So for small-scale problems, you can have substantial gradients, and this allows for training, but for large-scale problems, your landscape becomes exponentially flat, and exponential resources, exponential time is needed to train. Okay, so over the years, we have identified a number of sources of band plateaus. So the first paper on this was one by Jad McLean, where he showed that using an inappropriate choice in circuit, namely one that's too deep, could lead to band plateaus. We follow this up, showing that if your ansatz, your parameterized quantum circuit, is too expressive, can capture too many different sort of target solutions, this can lead to band plateaus. There was this nice paper by Carlos, Maria, and Nathan, where they showed that using an ansatz that was too entangling leads to band plateaus. In this paper, we showed that basically using an inappropriate, picking your problem incorrectly, having a problem that was too unstructured, involved too much randomness, you could have band plateaus. Marcos Reza et al. Showed that picking your cost function inappropriately could lead to band plateaus. So namely, if you're using a global loss, where you're basically measuring all qubits, that can have a band plateau, but if you have a local loss, things can be trainable. And finally, Sampson Wan showed that you can have noise-induced band plateaus, so hardware noise can lead to band plateaus. These two papers, in the nice way that science sometimes does this, came out at exactly the same time, with a unified account of all of these different causes of band plateaus, where they tie together all of these individual sources in terms of a sort of group theoretic, dynamical algebraic account of how these rise. Okay, so then in parallel to this hunt for the causes of band plateaus, people then went away and tried to come up with provably band plateau-free platforms. So again, this sort of evolved slowly in time of people piecewise coming up with new band plateau-free architectures. So one of the first ones, yes, as I said before, was if you have a local cost and if you have a shallow hardware efficient ansatz, so sort of nearest neighbor ladder type ansatz, then in the cost function dependent band plateau paper, they showed that this is provably band plateau-free. One of the next ones that came along was convolutional neural networks. So quantum convolutional neural networks were shown to be band plateau-free. Then certain Hamiltonian variational ansatzes or highly symmetrized ansatzes were shown to be band plateau-free. And finally, small angle initialization. So if you don't randomly pick your initialization angles, but pick them in some small range around 0, these were shown to be band plateau-free in these papers. Okay, so I've given you sort of, this is a lot of papers, and this is historically how this field has grown. It's grown by this sort of piecewise by piecewise analysis, where people figuring out slowly the causes of band plateaus and ways of avoiding them. So the question is there a common story to be told here? And actually, what we sort of started to notice recently was that there really is a sort of common factor between all these stories. And to see this common factor, it helps to take a step back and look at a standard variational quantum algorithm loss. So this is the VQE loss, where you take an initial state, you evolve it under parameterized quantum circuit, and then you do a measurement. And what you see is that this is just an inner product, either between the time evolved state and the observable, or if you sort of switch it around into the Heisenberg picture, the inner product between the initial state and your time evolved observable. So yeah, that is the loss expressed as an inner product between, i.e. a similarity measure between two operators. And crucially, these operators will be exponentially large, inevitably. Now, this should raise some red flags because we can expect that under general assumptions, the inner product between two exponentially large objects will on average be exponentially small and concentrated. So just think about two quantum states, two pure quantum states in some exponentially large space. Their overlap will generally be exponentially small. And so we expect this loss to generally be exponentially small or exponentially concentrate to a fixed value, depending exactly on what these two terms are. So this is our claim. All of the ingredients I spelled out before of the cause of the band plateau effectively amount to a curse of dimensionality, the difficulty in trying to compare objects in an exponentially large space. So to try and understand when, sort of more concretely, when band plateaus kick in and when they can be avoided, we need to ask the question, so let's think again about this form of the loss. So we're looking at the inner product between the state and the propagated observable. So to try and figure out when this can be big, when it can be small, when it's going to vary substantially with theta, or when it's going to be fixed to some value, we need to ask the question, where can this Heisenberg evolved operator go? So when can we avoid the exponentially large space? And these questions can be answered by computing the overlap between the Heisenberg evolved states and some basis for the Hilbert space. So these PJ terms are just basis elements, basis operators for the Hilbert space. So it could be Pauli's or whatever your favorite basis is. And the first thing to note is that if you have a global measurement, then even at very shallow depths, this global measurement, think about it as all z's on each qubit, can be transformed into exponentially many other measurements. So think about just all z measurements and then single qubit rotations. You can generate all possible tensor products or Pauli's like that. So this operator spans an exponentially large space. On the other hand, if you're looking at a local measurement and you've got a shallow depth circuit, then the light cone is going to restrict the Heisenberg evolved observable to only a polynomial space. So that is, we can actually only reach operators acting on a small number of qubits. And crucially, the observable is really important here. So we've got both are shallow circuits, but the choice of measurement operator changes where we can go. But of course, the circuit is important too. If the circuit gets deeper, then even your local operator is going to become a global one, and it's going to span an exponentially large space. And this is effectively a reinterpretation of the results in the cost function dependent band plateau paper. So we can see that global operators or local operators with deep circuits, you're going to be comparing exponentially large objects in an exponential space. And so we expect things to be concentrated. But if we have local operators and shallow circuits, then we can be living in a poly space and maybe things will be trainable. Okay, so let's just pin this down a little bit more. Let's take an observable and let's just expand it in terms of some basis. We can write it as sum of over lambda, c lambda, p lambda. And then we're going to define as b lambda as the subspaces associated to each of these terms as we Heisenberg evolve it backwards. So p lambda of theta is just going to be the Heisenberg evolved component of our observable. And then b lambda is going to be the subspace that this thing lives in. So then we can write out the loss in this form. So I've literally just substituted this expression into the term we had before. Now, the crucial thing to note here is that we're looking at the overlap between rho and p lambda of theta. And so all we care about is the bit of rho that lives in b lambda. So that is the subspace spanned by this thing. So we can just project down this rho onto the b lambda, and that's what rho lambda is going to be. And we can rewrite the loss like this. So now the loss is written as the sum of the inner products in the subspace you get from back propagating each of the terms in your observable under your circuit. And now the claim is that in general, if these things are in exponential spaces, you're going to be comparing exponentially large objects in exponential spaces, and things are going to be concentrated. But if any of these subspaces are only polynomially large, then some component of the loss arises from comparing objects in non-exponentially large spaces. And so you can get non-exponential concentration. Note here that the initial state is also important. So let's think about this case where you're confined because of a light cone to some polynomial subspace that is spatially localized. Now, if your initial state is too entangled, P lambda is going to be, that shouldn't be 0. That should be some like identity over D. Your reduced state is going to be highly, highly mixed. And so your loss is going to be exponentially suppressed. You're just losing all information. So you see that your initial state is going to have to satisfy an area law so that you actually have meaningful information when you take this inner product. And this is effectively a reinterpretation of the entanglement-induced bound plateau result. Okay, so if we do a case-by-case analysis of all the BP-free architectures and methods used in the literature, what we see is that actually all of these cases that people have gone through before and tried to prove absence of bound plateau results for, they actually live in classically identifiable polynomial subspaces. So, for example, so a lot of the cases, so the small angle initializations or the shallow cases, they're basically living in local subspaces. So adjacent qubits in some sense, either order 1 or log n. But some of the symmetrized ones live in symmetrized subspaces. So for example, this U1 equivariant case, this corresponds to the case where you have a particle number conserving gates. So you basically lived in a space with a fixed Hamming weight. And then your subspace is just going to be all operators in this subspace, in this fixed Hamming weight subspace. And crucially, one thing to notice here is it's the very proof of the absence of bound plateaus that allowed us to find these polynomial subspaces. So it might be the case that there are other bound plateau-free architectures that live in a poly subspace, but we cannot identify it. So there is no BP, but we cannot prove it. And I'm going to discuss this caveat more later. Okay, so we've established that all of these provably bound plateau-free architectures, so the type of architectures we think we need in order to allow for training, because we don't have exponentially vanishing gradients, and we've shown that they all live in polynomial subspaces. But then this is where sort of the phantom of classical simulability comes in. So a lot of the power of quantum computing is meant to come from the fact you live in some exponentially large space. But if you somehow reduced your problem to a polynomial subspace, maybe we can get away with classically simulating it. And actually what we see is that if we do a case-by-case inspection of all the U of theta that we have in these cases, so the U of theta for all of these provably bound plateau-free architectures, what we find is that the U of theta bit can be classically simulated. And so if we're dealing with a loss where the initial state and the measurement involves classical initial states and measurements, then the whole thing is going to be classically simulable. So I'm not saying anything particularly new here. So this was or is sort of increasingly discussed, but sort of hasn't or hadn't sunk in all corners. So let me just run through some examples. And I am not an expert on all of these simulation methods, but I will give you some reference and try and hand-wavily describe a few of them. So firstly, these shallow hardware efficient ansatz, so basically brickwise architecture up to log depth, or small angle initializations, quantum gentry modeling, which basically also just boils down to shallow hardware efficient ansatz, or the quantum convolution network. All of these can effectively be simulated using tensor networks. These cases can also be simulated using light cone methods. So effectively, you're working with the fact that you don't actually need to consider all measurements in one go. You've just got this light cone. And actually, you can just then simulate the unit tree within that light cone and drop off everything else. So that's been explored in some of these papers. My new favorite, and I should say that actually in contrast to the other ones, these methods don't have provable guarantees yet. But they're my new favorite because we've been working on them, but we weren't the first. Other people have done this stuff before. Clifford and tree-based methods. So the idea is it's effectively a Clifford simulation, but when you have non-Clifford dates, things branch, and this gives you like a tree-like structure. So these cases can also be explored with these methods. And then there's another family of approaches. So all of these symmetry-based architectures for avoiding barren plateaus can be simulated using broadly what is known as GSIM. So GSIM is a recent paper put out by the Lausanne team on sort of Lie algebraic method for classical simulations. And what it really does is it ties together a bunch of methods that are already understood for simulating highly symmetrized problems. So for example, take the UN equivariant case. So this is the case where you've got particle number conserving gates. In that case, what you do is you just project your initial state down onto your low Hamming weight subspace, and then you would project all of your gates that preserve particle number down onto that subspace, and then you can do your entire simulation within that subspace. And it's a similar idea for these other ones here, but based in different symmetry subspaces according to exactly what symmetry they're using. Okay, so as I said, each of these, if you sort of do a piecewise analysis, have their own classical simulation methods that can be used to simulate U of theta. And I'm not saying anything new here. What I am going to say that is new is that previously it was thought that if you had non-classically simulable initial states or measurements, then the fact that you could simulate the U of theta bit wasn't useful. You'd have a non-classically simulable initial state, and so you'd need to run the variational quantum algorithm on the quantum computer. What I'm going to say is that because of our analysis showing that all of these problems live in polynomial subspaces, you don't actually need to run that bit of the algorithm on the quantum computer either. But before I get there, let me just pin down a few different notions of classical simulability. And bear with me now, I'm not going to be precise at all in a sort of computer sciencey sense. I just want to give you a hand-wavy intuition. So classical simulability, we're just going to say a problem is classically simulable if it can be simulated on a classical computer in polynomial time. And then we're going to introduce this category called CSIM-QE, so classical simulation quantum enhanced. And what this category of simulation is going to be is it's going to be a simulation on a classical computer, but that classical computer can use data from a quantum computer. But it can only use data from the quantum computer in initial data acquisition phase. So it can't be used adaptively, it's non-adaptively. So you've got to run stuff on your quantum computer to collect some data, sort of to look forward a bit. It's going to be to project down your initial state onto the subspace you're interested in. And then the rest of it can be done classically. So this is, the crucial restriction is your amount of data from your quantum computer is going to need to be polynomial. So this is similar to BPP/poly or BPP/SAMP for those of you that like decision problems, or can be roughly thought of as creating a sort of classical surrogate of some kind of quantum problem. And then finally, we'll have quantum simulation, where quantum simulation is just running stuff on the quantum computer. Okay, so I want to stress that all problems that are either in CSIM or CSIM-QE, so classically simulable or quantum enhanced classically simulable, do not require running the parameterized quantum circuit on the quantum computer. So either quantum resources are completely unnecessary, as in the case of CSIM, or they're only used in some initial data acquisition stage, as in the case of CSIM-QE. So a quantum advantage is possible for problems where the loss can be simulated only if we have access to a quantum computer. So that is for any problem that is not in CSIM-QE and is in, not in CSIM, but is in CSIM-QE. So basically, it's got to be solvable on a quantum computer somehow, but it's got to be not classically simulable. And then, of course, an advantage from running the parameterized quantum circuit itself on quantum hardware over just collecting data to create some surrogate and then training classically, that's only possible for problems that are in QSIM and not in CSIM-QE. So it's only if a problem is not in CSIM-QE that we actually need to run the parameterized quantum circuit on the quantum computer. Okay, so back to what I was saying. So from a few slides back, I was saying that the loss can be written as the sum of inner products in each subspace of the back propagated. So we take the observable, we split it into a bunch of terms, we back propagate each of these terms in the Heisenberg picture. We then look at the subspace that these back propagated terms are in, and we can compute the loss as the inner product between the back propagated operators and the initial state projected down into these subspaces. Okay, so in order to compute the loss, we just need to compute a basis for the initial state for each of these subspaces, and then project the initial state into that subspace. So if we have a classical representation of the initial state, we can compute these projections classically, and then actually computing this whole thing is just going to be in CSIM, because as I said before, the U of thetas for all of the cases that are provably bound plateau free, they are classically simulable. If we do not have a classical representation of the initial state, then we can't do the projecting down onto rho lambda classically, but we can do this on a quantum computer. So that is, for example, in the case of the hardware efficient ansatz, you'll just be projecting your initial state down onto local subsections, basically doing local tomography. Okay, and crucially for provably bound plateau-free architectures, these B of lambdas are going to be polynomial subspaces. So this only takes a polynomial number of measurements, and this means that the problem is in CSIM QE. So yeah, for the example of the shallow hardware efficient ansatz, this is just going to amount to measuring poly n many Paulis acting on log n neighboring qubits. And then you can just do the U of theta bit using reduced light cone methods to simulate the U of theta, and then you have everything you need in order to compute this loss. Okay, so then again, we do a case-by-case analysis of all the provably BP-free architectures and methods used in the literature. And what we see is that all the problems known in polynomial subspaces are classically simulable, though potentially require data from the quantum computer if your initial state is non-classically simulable. So yeah, as I said before, these shallow hardware efficient ansatzer, you're going to be doing things like local tomography or Pauli classical shadows, and then plugging in either light cone methods or tensor network methods. On the other hand, if you're using a highly symmetrized case, you might be, say, projecting down into the low Hamming weight subspace you're interested in, and then doing symmetry preserving operations to do the simulation. So punchline is, none of the standard problem instances with provable absence of bound plateaus does the parameterized quantum circuit itself need to be implemented on the quantum computer in order to estimate the loss in polynomial time. It's always going to be in CSIM, so classically simulable, or quantum enhanced classical simulation. It's maybe worth here drawing a parallel between this and some of Robert Huang's old stuff on power data and quantum machine learning. So this paper here, he's talking about how actually classical machine learning with quantum data is a super powerful paradigm. And that's in a sense what we're advocating with CSIM QE, that you're going to use classical machine learning techniques to optimize a surrogate that you're going to generate using a quantum computer to get your data from the quantum computer. Okay, so I don't know how many of you are actually interested in VQAs, but we certainly went on a sort of emotional roller coaster as we went through discussing this work. We initially thought it had to be wrong and then questioned whether we were trying to kill our field and get us out of jobs. We then started thinking whether maybe we'd have to do fault tolerant algorithms now. And then we started realizing that there are an absolute ton of caveats to our arguments, and that actually raises loads of new questions. And we now feel pretty comfortable and happy with it because actually we've got, we think, a better understanding of how things lie and see lots of sort of new opportunities for research directions. Okay, so I'm going to move on to sort of the interpretation and discussion bit in a second, but before I do that, I just want to recap the concrete bit. So what we've actually shown that is, I think, not so debatable. So firstly, what we've done is we've taken a ton of bound plateau-free techniques and architectures in the literature and shown that in all cases, basically the proof of bound plateau freeness, is that a word, bound plateau freeness, boils down to showing that the problem lives in a polynomial dimension subspace. And then what we've done is we characterize the joint action of U of theta on the basis element of all the terms in our observable that lead to the polynomial subspace, and we've identified what O's and rhos we need in order to ensure that we're in that subspace and things don't exponentially concentrate. And then finally, we have studied whether we need a quantum computer to estimate or measure the component of rho or O that's in the relevant subspace, and we've shown that we've argued that this determines whether or not we are in CSIM or CQE. Okay, so now let me discuss things we are not claiming. So first things first, we are not saying that if the loss function is not exponentially concentrated, then it will be classically simulable. So I've done a case-by-case argument showing that all of the commonly encountered provably bound plateau-free cases that are explored in the variational quantum algorithm literature do fall within our framework of living in polyspaces and so being either classically simulable or classically simulable with quantum data. But we can, of course, using Shor, so maybe we don't care about this counterexample too much, construct counterexamples of non-concentrated losses that are not classically simulable. So as I said, this involves cooking Shor's algorithm into a rather contrived problem. I don't think we're really that interested in this counterexample, but it's important to stress that we have this counterexample. So we are not saying that exponential concentrating necessarily means things will be classically simulable. And I say it's rather contrived. It also does not really resemble current mainstream variational quantum algorithms. But it maybe can give us some nice insights, because what it does is it shows that our whole argument is based on the observation that comparing objects in exponentially large spaces is hard and leads to concentration. In these cases, things live in an exponentially large space, but the circuits are more structured. And it's really the structure that allows us to avoid exponential concentration. So based on this caveat, I think sort of one opportunity that this raises is that maybe we could investigate some more sort of fault-tolerant inspired variational quantum algorithms, because fault-tolerant algorithms, they explore large Hilbert spaces in a clever, structured way. And maybe by doing that in a variational context, we can also manage to construct some interesting cases of non-exponentially concentrated, non-classically simulable algorithms. Okay, that's caveat one. Caveat number two is that our argument applies to losses of this form. So initial state evolved under some unitary and then some observable. It also applies to simple generalizations of this, where we sort of sum over different initial states and different observables, or if we do classical post-processing of this. But some forms of geometric models do not fit in this framework. So, example, Boltzmann machines. Also, sampling computing expectation values seem to have different complexities. So this means that one, our argument might not apply to certain models, and two, even in cases where it does apply to models like this, a QC might still be needed to sample solutions. So an example of this would be QAOA. So QAOA, the ultimate solutions are samples from your solution. You might be able to train your QAOA using some of the classical methods that we've been discussing, but actually to get samples out in the end, you might need to go and run your parameterized quantum circuit on the hardware. Okay, so opportunities here, investigate more, again, fault-tolerant inspired variational algorithms, perhaps investigate Boltzmann machines. So one thing that's nice about Boltzmann machines is that you can train them cleverly, but then ultimately, again, to get the samples out at the end, you have to prepare these hard thermal states. And that's where you're going to draw on potentially your fault-tolerant algorithms for pairing thermal states. And we should also maybe investigate other learning paradigms that don't fall into this framework. Okay, another very important caveat is that of special initializations. So both bound plateaus and in places our notion of simulability are average case notions. So bound plateau is saying that on average over the landscape, gradients are exponentially small. But this does not preclude that you could have substantial gradients in small subregions. So exponentially small proportion of the total space, but still a substantial proportion of the space, you could have some gradients. Also, some of our notions of simulation, and this dives into subtleties that I've not covered here, but I'm happy to discuss in discussion, are average case notions of simulability. And that means that when we say things are simulable, in certain cases, so specifically the cases of quantum convolutional neural networks and small angle initializations, it might be possible that we can't classically simulate in small subregions. And if those turn out to be the really interesting subregions where the solution lies, then our argument breaks down. So all of this suggests that maybe special initializations, also known as warm starts, could be the way forward. So one opportunity here would be to investigate more clever warm start strategies. And I'm not going to talk more about here, but we've got a few things in the works that should hopefully come out soon on this. This is also one of the topics I would say that caused the most arguments and disagreements among the co-authors. So Marco is probably the most skeptical about warm starts currently. Manuel, my student, is super pro warm starts. I'm somewhere in between. So this was actually a GIF that Marco did on the GIF meme. Marco did suggesting that we're coming for warm starts next. So that's entirely true. I think we have both good and bad news when it comes to warm starts, and there's a lot more to investigate. Next one. Okay, so crucially, this isn't a dequantization. So the quantum computer is still crucial. So for any problem with non-classically simulable initial states, so for example, QNN that you're trying to use to classify some ground states of some interesting material, then the quantum computer is very, very much still needed to collect the data. And in fact, all we've said so far is that this sort of CSIM-QE, that it's simulable in terms of CSIM-QE. So it's simulable using a polynomial amount of training data from the quantum computer. But also just doing your VQA standardly is going to require most polynomial access to your quantum computer. So in both cases, you've got polynomial access to the quantum computer. And what we really need to do now is compare these polynomials and see which is better. But we are advocating a different ways of using the variational we're advocating a different way of using the quantum computer. So we're advocating at the moment, or at least for a problem in CSIM-QE, that you can get all of your data at first and then do the rest classically. And I think the advantage of that is that you can then plug in more classical machine learning methods than you would if you were running your VQA directly on the hardware. So specifically, you can do things like backpropagation for gradient updates. So opportunity here, one, there could be provably polynomial advantages for actually running a parameterized quantum circuit on the hardware. Or it could turn out, though I don't know, a bit less skeptical of this, a bit more skeptical of this, that there are practical advantages just from running it on hardware. And certainly, and I'll move on to the next slide, there could be non-provable advantages from running on hardware. We don't need to be able to prove anything just for something to actually turn out to work better. The other thing to say here is that actually there's all sorts, we're advocating this kind of slightly new way of doing variational quantum algorithms, where you get your data first and then you train classically. And actually to properly make use of this paradigm that we're trying to sell, there's lots of research that still needs to be done on, firstly, how to effectively extract data from the quantum systems. So this is going to be things like new shadow techniques. And then also more research on classical simulation of quantum systems and machine learning models for quantum problems so that we can do the classical bit well. So I think there's lots more to investigate there. Okay, and I think this is my final caveat. So crucially, everything I've said relies on proofs of absence of barren plateaus. But it could turn out that sort of heuristically, people manage to find large gradients and train, but we can't prove that it's possible to train, they just find it. And in such cases, you probably wouldn't be able to identify a polynomial subspace. And if you can't identify your polynomial subspace, then our trick for knowing how to classically simulate just falls apart. And I think people who are a fan of this approach argue with sort of comparison to the classical case. They say classical machine learning, we don't bother proving stuff's going to work, it just works. And I think this is a really tricky argument. I think it's impossible to argue against it. I sort of almost like to make the comparison with faith being the best argument for God here. It's an impossible one to argue with, and it really comes down to a matter of perspective. That said, one thing to remember in this case is that precision is much more expensive on a quantum computer than it is classically. And also the fact that classical machine learning is so successful means we are quite a hard bar to beat. So I think people in sort of who fall down this line are effectively praying to the gods of classical machine learning, and we'll see who ends up right in the long run. I genuinely don't know. Okay, that's me onto my conclusion slide. What are we to draw from this? So we've argued that provably barren plateau-free architectures are either classically simulable or classically surrogatable. So that is classically simulable after collecting some data from a quantum computer. And we can interpret this result in different ways. So we can see it as something positive. The algorithms are potentially easier to implement. We don't need this loop. we can push even more complexity onto the classical devices. And if you're someone who wants to run stuff on the quantum hardware the entire time and do it didactically, we might even be able to prove polynomial advantages for doing that. We can also push back against our argument. We know that we've got the Shor counterexample, and maybe there's some more fault-tolerant algorithm-inspired type ansatzer that we can also prove exponential advantages for actually hybrid variational quantum computing with, but in more interesting setting. For this, I think we need to, try and draw more inspiration from sort of conventional fault-tolerant algorithms. And then sort of the final response is the sort of the true chaotic evil heuristic path. And this is always a legitimate response, but one that I think everyone will relate to in different ways. We can't prove the presence or absence of bound plateaus, but maybe things will just work out in the end in the way they did classically. So lots of different interpretations of my results, and happy to discuss things if you have any questions.
Awesome. Thank you so much for that very interesting talk. Do we have any questions, comments from the audience?
Yeah, I have one. So you mentioned the Shor's algorithm as a counterexample, but I couldn't see on myself which part of Shor's algorithm behaves.
Okay. No. So fine. No. But it's not obvious. What we do is, are you familiar with there's a game in quantum machine learning at the moment where people cook the discrete logarithm problem into a machine learning task and manage to prove a quantum advantage that way. So it's in the same spirit of that. If you want, I mean, okay, it's buried in the appendix. It's very contrived. Can you see my screen, by the way?
Yes.
Yeah.
So what we do is it's actually it doesn't even need to be discrete logarithm. It's any sort of, you can just use any cryptographic assumptions. So what we do is we consider this circuit that basically we have an initial layer that prepares a random computational basis state. And then we have U being a fixed depth quantum circuit that implements a Boolean function. And what we consider is that it's going to implement basically this Boolean function the following way. So it's up to some estimate, it can always do the Boolean function to some accuracy. And then based on the fact that basically Boolean functions are hard to estimate classically, we can argue that this is going to be a hard loss. Okay, oh, sorry. And then we're going to consider this loss, which is basically just for different theta values here, you're going to get a random computational basis state. We're going to consider actually just a discrete set. So this means you get a fixed a computational basis state. And what this does, this loss then basically estimates this Boolean function. And then we can use the fact that Boolean functions are meant to be hard to estimate. Sort of certain cryptographic Boolean functions are hard to estimate, to argue both that you're not going to be able to simulate this classically, even with advice. So it's basically, it's not in BPP/poly. And then also the fact that the Boolean functions are hard to estimate classically means that this is going to have a large variance. And so you can basically connect actually the large variance with the hardness to simulate classically. So I appreciate that was very quick, but sort of that's the broad idea of how we cook the problem in, and it doesn't really look like a variational quantum algorithm in normal terms.
I see. And that Boolean function is sort of in the Shor's algorithm.
Yeah, exactly. So I said Shor to simplify it. It's really, it could be a discrete log, for example. That would be the obvious one to use here.
Okay. Thank you.
There's a question.
Yeah, let me go to the question in Zoom. Thomas?
Yeah, thanks. And thanks for a nice talk. It was really interesting. Yeah, so we've also looked a bit into barren plateaus, but so my sort of kind of general question is still, why are we so fixated on the barren plateau question? Because I mean, it's in a sense, it's just about the first optimization step, right? Once you have optimized a little bit, right, you're out of this question of like looking at random angles, and so maybe also going to your point about warm-up schemes. So couldn't you, for example, just start with a very like small, simple circuit, highly structured circuit, which we can efficiently optimize even classically. And then just step by step, sort of we add further gates and go into the regime that you can't classically simulate anymore, but you also follow, like you're always following sort of a tractable path where you never encounter any barren plateau issue.
Okay, so I think these are all the questions we should be asking. I think the fact that on average over the landscape with exponentially high probability the landscape is flat still tells us that there are large regions where things are completely flat. So it's not just about initialization, it's also the idea that you might wander into these flat regions. So for example, these small angle initializations I was talking about basically make use of the fact that around identity you have gradients, and if you don't go too far away from identity, you're also going to have gradients. But in most interesting cases, your solution is not going to lie there. Presumably, if it did there, that's boring. It's going to be classically simulable. So then the question is there, okay, so are you going to need to cross part of the barren landscape in order to get to your good solution? Or will you get lucky and will that? So my intuition historically was, yeah, you're going to have to cross this barren landscape. There's no chance in hell. You can start in this nice region of identity, and then wherever you're trying to get to, odds are you're going to have to pass some barrenness. I mean, that's not the only possibility. It could be that there is like, you're very lucky and there's some really nice fertile valley that somehow leads you towards a solution. That is possible, or at least it's consistent. And if that's the case, odds are we're not going to be able to prove it. Odds are that it falls into this one, really. Like, it's just having faith that we're going to find that somehow everything will work out. And I would also just say that people have been really struggling to optimize variational quantum algorithms. I mean, people haven't done anything that big. Even just sort of classical simulations with shot noise, people aren't going that big. So I think no one knows how likely it is, whether you're going to have this valley or whether you're going to have to cross this barren plateau. The evidence right now doesn't look amazing. I think there's reason to be pessimistic. Also, sort of it's exponentially small probability in some sense. But then you can always fall back on classically stuff just works out and just hope that that's also going to be the case.
Yeah, thanks. Yeah, I agree. You might have to cross these flat regions, and that might be, it would be interesting to any techniques sort of to answer this question or analyze whether this is generally the case or not. Right?
Yeah, and one thing I'd also say is that if you then show that you have some funky region that's weird shaped, that's polynomial, that you have gradients in. So it's got to be a polynomial subregion that you have gradients in the whole space, because we know that talking about it, assuming we've got a barren plateau over the whole case, in theory, you could still surrogate that potentially if you can approximate where this region with gradients are. So it could be that even if there's some nice little path that takes you towards the minima, that maybe the CSIM-QE way of training is the way to go about it. Sort of question mark. I think that's still to be investigated.
Thanks.
Awesome. Henry?
Yeah, this is a very interesting talk. Do you know if people have looked into using classical machine learning methods to kind of learn circuit structures that can avoid barren plateaus?
Yeah, people have done that, but it doesn't really help as I see it, in that fundamentally any of those, you've got to train on cost differences. Basically, you've got to try and figure out whether this architecture gives you a lower cost than that architecture, or does adding this gate lower your cost, or does it not lower your cost? Does changing this make things flatter or not flatter? And so if you don't have gradients, just using a more clever optimization strategy, I don't think really helps. So I think it can be shown that things, you mitigate the problem slightly. You potentially come up with slightly cleverer architectures, but fundamentally you've still got the exponentially large space problem and the sort of the lack of a structured search strategy.
Awesome. Any other remaining questions, thoughts?
Okay, so in that case, I think we'll say thank you, Zoe, especially for staying up so late to talk with us today. And let's give another hand.
Cool. Thanks for having me. See ya.